Hello everyone, so this is part two of the homework which I set you. I'm just going to go through the nasty question on demoivres. I say nasty, it's not too bad actually because these questions do get quite samey, provided you don't get them muddled up. It's B part one I'm talking about here. Provided you don't get the two techniques which are both quite long muddled up. The one where you basically they're kind of back to front techniques. The one where you express a multiple of the angle in terms of powers of the trig function, or the other way around, the one where you express a high power of a trig function in terms of multiples of the angle. This one's obviously the former case, not the latter, but it's easy to get the methods muddled up. That's what I think about this topic. The actual induction to prove demoivres isn't actually that difficult. It might sound fierce because it's a proof, but it really isn't too bad. So, like with any inductive argument, I'm going to start with a base case. The base case is trivially true, n equals 1, yeah, because we're only proving this for positive integers. It does actually work for rational integers. It even works for complex exponents in certain cases, I believe. In fact, if you want to know why cosh theta is cos I theta and sine theta is I minus I sine I theta, try plugging in I into that power there and you're going to see what pops out. That's a little invitation for some joyous mathematics here. Try plugging in n as I in this formula and you'll see where cosh and sine come from. Okay, anyway, let's get on with it because that's not what we're here to do. I'm just going to run you through these. So base case n is 1. You've got the left hand side obviously equals cos theta plus I sine theta. And the right hand side, well, that equals cos theta plus I sine theta. Make it look like you have actually considered what's going on when you're plugging in the base case, because I mean it's just trivially true. You know, hence the result is true for n equals 1. The result holds for n equals 1 for the base case, or basis step, whatever they call it nowadays. Okay, assume true for n equals k. That's what always happens next in a proof by induction. I.e., now write it down again, yeah? You know, because this is part of the argument. You've got to remember, with a proof by, particularly a proof by induction, this is part of the argument. Cos k theta plus I sine k theta. Oh, k theta. Then, for n equals k plus 1, in other words, for the next term, we have, what do we have? Let's see. Well, we're going to have cos theta plus I sine theta to the k plus 1. And now you always use the result which you assumed true in a proof by induction. Yeah, if you're not using the result which you assume true, you're doing it wrong. That's to the power of k, and then we're going to multiply it by cos theta plus I sine theta, and writing it like that allows me to use the result I assumed true. Also, think about where you're heading towards in a proof by induction. And we're heading towards, we hope, k plus 1 theta in the arguments. We want k plus 1 theta appearing there because that's what demoivres is telling us. Multiplied by, let me budge up a bit on the screen because I'm running out of space, cos theta plus I sine theta. Now the trick with this particular proof by induction is compound angle formula essentially. Now when we're multiplying out, think what you're going to get. Let's look at the real terms first. You're going to get cos theta, cos k theta. Yeah, that's one real term. Now you're also going to get a cos k theta times an I sine theta, but I'd much rather look at the real parts here. Now the other real parts you're going to get from doing I times I, which is I squared, which is minus 1. So that's going to be minus sine theta sine k theta. Okay, I've done the real terms. Now let's do the imaginary terms. Plus, plus I cos k theta, well, plus I times cos k theta sine theta, plus, and then you're going to get the other one from doing that times that, sine k theta cos theta. Lovely. This is now just a straightforward application of the compound angle formulae. Cos minus sine sine. We add. We're going to be doing cos of theta plus k theta. Well, that's the same as theta times k plus 1. So let's call it k plus 1 theta, all within the cos. Plus I times sine. Well, sine works the right way round if you like, but you're still going to be doing theta plus k theta here, and so you're going to have k plus 1 times theta. This is what we were hoping was going to happen in our proof by induction. It's what we were aiming for. And so at the end, I'm just going to say some inductive remarks. I like writing a lot here. I really do. Make it clear to the examiner you understand how induction works. I'm just going to say, but this is a result with k plus 1 substituted for n. So what have we established? Well, we've established truth for n equals k. Hence, if it's true for n equals k, and it was only assumed true, but if it's true for n equals k, it must be true for n equals k plus 1. It must also be true. In other words, if it's true for one term, it must be true for the next term. As it's true for n equals 1, it follows by induction that it's true for all positive integers. For all m which are members of the positive integers. There we go, by induction. Just to make it real clear we understand what we're doing here. Okay, that's Demoivre's proved inductively. You can also prove it for rational exponents and even for complex exponents, like I say, which is amazing. It's a cool result. Okay, use this result to show that this is true. Well, the way we want to do this is we want to say, okay, well, firstly note that cos 5 theta plus I sine 5 theta is going to be equal to cos theta plus I sine theta to the power of 5 by Demoivre's, yeah? Now, before you do this, let C equal cos theta and S equal sine theta for your own sanity here. Because what we can say is we need the imaginary component of this expansion, yeah? Because the imaginary component will be sine 5 theta. Let's just expand it first, I guess. Let's just say cos 5 theta plus I sine 5 theta. And let's just go about the expansion. We've got c plus is to the power of 5. So we're going to have c to the power of 5 plus 5 times c to the power of 4 times by is to the power of 1, if you like, plus 10 times c cubed times by is squared. You might be thinking, where am I getting the 1, 5, 10, 10, 5, 1 from? I just know that row of Pascal's triangle, but by all means use binomial coefficients 5 choose 0, 5 choose 1, 5 choose 2, etc., etc., if you feel more comfortable doing it like that. Okay, plus 10 c squared is cubed plus 5c is to the 4 plus is to the power of 5. Done. Okay, now we only want the imaginary components, yeah? Well, let's actually do one more line of working so we can work out what the imaginary components are, because you're going to have c to the 5 plus 5 c to the 4 is. Now, here's where it gets interesting. I squared is minus 1, so this is going to be minus 10 c cubed s squared. I actually don't know on that one because that's one of the real components, which, aligns with cos 5 theta, if you like. This is going to be minus, I cubed is I squared times I, and I squared is minus 1, so minus 1 times I, that's minus I. So there's still going to be an I left in this one. You're going to have minus 10 I c squared s cubed. And then this one, I to the power of 4, is I squared, which is minus 1, but then you're squaring that again, which gives you 1. So this is going to be 5c s to the 4. And then I to the power of 5 is actually just I, so you're going to have plus I s to the power of 5. It's real easy to mess up something like that. So in the past, students have told me it's helped them to go I to the power of 1 is I squared is minus 1, and have this kind of written down in the margin. Because it just kind of loops around after a while, doesn't it? And then you're back to the start and it goes right the way around like that. I minus 1 minus I 1. I minus 1 minus I 1. And so on and so forth. It literally just hops round the Argand diagram, doesn't it? Rotating 90 degrees each time, because if you multiply by I, you're actually rotating 90 degrees. Okay, so we need the imaginary component of this. How am I going to notate that? I'm just going to jump straight to it. sine 5 theta. Well, that's just going to be, just say, so we need imaginary terms. So sine 5 theta is going to equal, now if we just ignore the I, because sine 5 theta had an I on it, we're going to have 5c to the 4 s minus 10 c squared s cubed, because we need that one, we need that one, and we need the last one, plus s to the power of 5. Okay, this is the old c is 1 minus s squared, so that's going to be 1 minus s squared squared. This is going to be 10 times 1 minus s squared times by s cubed plus s to the power of 5. Do this a little bit carefully. That's going to give us 5 times 1 minus 2s squared plus s to the 4 times by s minus 10s cubed plus 10s to the power of 5. Be careful with that. Plus another s to the power of 5. Always running out of space here, aren't I? Move that down a bit. I need that for the integrals later. Okay, and what have we got here? We've got 5 minus 10s, 5s, I apologize, minus, because this is all being times by s, minus 10s cubed plus 5s to the power of 5 minus 10s cubed plus 10s squared to the power of 5 plus s to the power of 5. My 5s and s's look really similar, which really is a problem. 5s to the 5 plus 10s to the 5 is 15s to the 5 plus 1 more, 16 sine to the power of 5 minus 20s cubed. I really should be doing that good habit I've got of ticking them as I've gone, plus 5s. And I believe that's the result we needed. A is clearly 16, B is clearly 20, C is clearly 5. If you want to know how I checked this, I actually had my calculator in degrees at the time, but these results are true in degrees or radians. But I thought, I know what sine 30 is, it's a half, so I plugged in theta equals 6 into this in my calculator, and sure enough it came out as a half, which I thought was very satisfying. So I'm just going to write it out in full at the end, just so the examiner doesn't, cheek me and give me one less mark than I deserve. Okay, there we go. So it's pretty obvious what A, B, and C, I've found those integers. Okay, part 2. What makes me laugh about part 2 is this is so much quicker if you just use small angle formulae. If you use small angle formulae, is it not obvious that sine 5 theta over sine theta? Well, theta is small, so you're going to be doing 5 theta divided by theta, because sine x roughly equals x when x is small. 5 theta divided by theta is 5. So this should come out as 5. And indeed it does, because if you've got 16 s to the, well, if we just take our last expression and just divide it by 5, sine theta, sorry, you can see you're going to end up with a sine 4 theta here, a sine squared theta here, and a 5 on the end. Hence, when theta is small, because sine of 0 is basically 0, this just goes to 0 and you're left with 5 on the end. So we can just say limit as theta tends to 0 of, and let's just divide that all by, well, I can just see it in my head now how the answer is going to arrive, and it kind of annoys me when I've got to write lots of stuff down, but I better, just to make sure I get the answer. All divided by sine theta equals the limit as theta tends to 0 of 16 sine to the 4th theta minus 20 sine squared theta plus 5, which equals 5 as sine of 0 equals 0. Yeah, done. Okay, right, that was that one. Quite a fun question that I thought. So yeah, watch out for ones like that. This one, okay, so what have we got here? Looks like we've got one of these improper integrals. Let's go down the page because I just need more space. It's that complex numbers one. It was always going to take up a lot of space. Complex numbers do. There's a lot in that chapter. There really is. Okay, so let's do part A. I'm doing this. Certainly the way Edexcel massively encourages you to do it is say, okay, what we need is the limit as t tends to infinity of the integral between t and 0 of 1 over 1 plus x to the power of 5 dx. Yeah. Now this is of the form a plus bx to the m. And so we can just use the formula we've got, which is increase the power by 1. Oh, I don't need an integral now. provided n isn't -1, and it's not here, it's -5. Divide by that, and then divide by the coefficient of x and the new power. That's what I'm going to do, plus a constant, yeah. So I'm just going to have, in brackets, 1 plus x to the -4 divided by -4 between t and 0. And don't forget, we're thinking about t tending to infinity. Okay, what does that give us? Let's actually plug it in. Well, once again, we're still thinking about the limit as t tends to infinity. Keep writing that down in these kind of questions, yeah? Otherwise, the examiner's going to, cheat you and not give you a mark. Okay, so what have we really got here? That's supposed to be a 4. Let me just write that out again. My handwriting costs me marks, it really does. Okay, so what do we got here? We've got 1 over -4 times by 1 plus x, or 1 plus t if I plug in the t now, minus 1 over -4 times 1 plus 0. Yeah? Now, we'll plug both of them in. As t tends to infinity, this first term is going to tend to 0. You're allowed to use the fact that 1 divided by infinity is 0. So what we've really got here is minus a quarter, which equals a quarter. Yeah? The nice thing is on questions like this, I'm just going to try this on my calculator, but if I was to type in this actual integral, why is it not letting me? Oh, I think it could because I'm in complex mode. If I was to type in this actual integral, 1 over 1 plus x to the 5, I'm just trying to show you a way of checking your answer here, and sticking a really big number at the top. Hopefully, it will be very, very close to 0.25. Let's have a look. It's just taking me a moment. I'm just like doing this for my own sake as much as yours. 0 on the bottom. Oh, and let's put 999, 9999999. That sounds like a big number. Okay, I've let it think about it, and I've just realised that something's definitely gone wrong here. What's gone wrong there? Because I ended up with 8 times, I've ended up with an incredibly small number. In other words, it looks like it's not converging. Let me just quickly check the mark scheme. I'm pretty sure that does converge to a quarter. It does. So I wonder why my calculator struggled with this. Let me try. Have I typed it in wrong? I'm going from 0 up to a very big number, yeah, and it's 1 over 1 plus x to the 5. I was hoping that this would be a way I could kind of, check my answer. Let me just try not to be so extreme. I don't know why it wouldn't work with that though. Wonder if it's the radians mode shouldn't matter because this is nothing to do with radians. My calculator's having a really good think about it now, so I've obviously really baffled it here. I think I might have broken the calculator actually. Let's try and find ways that we can check our working though here. Do you know what I've said this time? This time I just chucked in 999. Before I chucked in 999 million. But this time it came out with the answer 0.25. So I'm pretty happy with that. So it looks like you can check it, but in some cases, if you go too crazy on the top value, something weird happens. Don't know why. Okay, this next one. What have we got here? We've got infinity and 2. And we're trying to see if this converges or not. Remember, we don't know if it's got a finite value. Okay, kind of annoying that they'd maybe do it like this, because I know a better way to do this one, which is just like, can I just show you the better way of doing this? That's exactly the same as that. In other words, the bottom differentiates to the top, so the answer is ln of the bottom. Between infinity and 2. Yeah, but that's not what they said we should do, so we're going to have to do as we're told. That's supposed to be an L, by the way. That's supposed to be a ln. So it's the ln of x, this one. I know this one. It's an old classic. But yeah, anyway, we'll do as we're told, I guess. I hate doing as I'm told. Okay, so let u equal ln x du by dx. This is obviously a substitution, is 1 over x. So du is 1 over x dx. Okay, right, so we've got a 1 over x dx in there, because there's a 1 over x there, dx. And so what we've got is 1 over u, and I've swapped the 1 over dx with a du. That's nice. And now think about your limits. Okay, these are the limits for x. Ln of infinity is basically infinity, because ln is an ever-increasing function, so this will still be infinity. But this is going to be ln 2. Now we can integrate it, so we get ln u between infinity and ln 2. Now the problem we're going to get here, oh, and I should be being really careful, shouldn't I? I should be doing limit as t tends to infinity. Apologies, people, you must be disgusted. So let's put a t there. So here we're actually going to get a ln t up here, which is fair enough. It's still going to look a lot more obvious what's going on. Limit as t tends to infinity of all of that. Here's the limit as t tends to infinity. Nobody likes writing this stuff down, but you have to, because it's a more solid argument. It's about like the subtleties. There are some situations where you can get misled if you don't do it. Okay, so okay, what's happening next? So limit as t tends to infinity, and I should have a t there, I'm sorry, beg your pardon, of ln t minus, oh, sorry, ln of ln t, because this should be ln t. So ln of t minus ln of 2 minus ln of 2. Magic. Okay, right. It's the ln of infinity. Infinity, if you try and learn it, you still got infinity, because, I mean, look at it like this. Basically, if you take natural log of infinity, well, when x is at infinity here, this just keeps increasing, so it has an infinite answer. It's a very slow growing function, but it does, you know, if you're taking something arbitrarily large, the output will be arbitrarily large, even if you do it twice. And so this clearly diverges as ln of t tends to infinity as t tends to infinity. Yeah, I shouldn't really put equals. So there we go. It diverges. Bit of an anticlimax, that one, really, wasn't it? I prefer it when they converge. Everybody prefers it when they converge. Okay, this one. Sorry about this, because I need to apologise. It actually covers one type we haven't seen yet. Although, if you're blindly following the formula book, then you would have been fine. So let's talk about it. Okay, like I've said to you before, whenever there's a quadratic, inside or not inside a square root, you want to complete the square. That's the trick. So take out the 1 over root 2 and leave in there root of x squared plus 2x plus 3. Next step, complete the square. So you can have 1 over root of x plus 1 squared plus 2, I think, dx. Next step, okay, go to the formula book and think, what gives me the answer to root of stuff squared plus some more stuff? It's this one, R shine. This is what I mean by it's one you haven't met yet. You might be able to do it with actually, if we shall I do it already? Shall I do it with a substitution? You hate substitutions, don't you? So I'm going to do it with a substitution. I'm going to make myself do it. What's going to be the cool substitution here? Well, if we use 1 plus tan squared is sec squared, let's use that idea, because then 2 plus 2 tan squared is 2 sec squared. So in other words, I want my x plus 1 to be equal to, by the way, this is definitely not the quick way, definitely not. And if you just wrote 1 over root 2 r shine of you know what you need to do here of x plus 1 over 2 or root 2, whatever it is, then that's fine. That's absolutely fine, good for you. But I just want to show you this just in case you're interested in how these substitutions work. I'm going to try and pick something which, after I square it, equals 2 tan squared. So root 2 tan theta should do the trick, because then dx by d theta is going to be root 2 sec squared theta. The 1 just cancels over here, you know, it'd be nothing. And so why does this make this nice? Well, we're going to get 1 over root 2. I'll change the limits in a second. We're going to get 1 over, right, this is 2 tan squared plus 2, which is 2 sec squared, which is root 2 sec theta. But we're going to multiply it by, well, dx can be swapped with root 2 sec squared theta, d theta. And that equals, take out the 1 over root 2, make this a half. Let's change the limits as well. These are limits for x, remember. So we're going to get 2 over root 2, that's root 2. So that would be arctan root 2. And then here, if x was 0, this would be 1. This would be arctan of 1 over root 2. Cool. Okay, right. So what have we got here? We're going to be having, I've taken out the root 2 there to make that a half. This means we're actually going to, oh, I should have just cancelled it actually and kept it as 1 over, that would be far more sensible. 1 over root 2. And then what does sec theta integrate to? Well, it actually integrates to ln of tan theta plus sec theta. It's in the formula book. Let me just quickly take a picture of it so you believe me. It's in the formula book, this. Integrate, is it in the, it's in the formula book under A-level maths, actually. Where is it? Where are you? Where are you? Yes. Let me just take a picture of it so you can see I'm not lying. I'm just showing you a crazy way of doing it. Good for you if you just use the result in the formula book for R-Shine, because I think you're doing hyperbolics at the moment anyway, aren't you? So here we go. See, the integral of sec theta is just ln sec plus tan. And I can prove that to you as well, but not today. I think we've done enough on this one. So this is going to be ln of sec theta plus tan theta arctan of root 2 and arctan of 1 over root 2. Now I've got a sneaky way of handling these limits actually as well, because, well, firstly, tan of arctan of root 2 is just root 2, yeah? So this is going to be 1 over root 2 ln of, now I wonder what sec theta is when tan theta equals root 2, because 2 over root 2 is root 2, yeah. So if tan theta equals root 2, then you're going to be doing root 2 squared, which is 1 plus 2, which is 3. So sec theta is going to be root 3. So this is actually going to be root 3 plus root 2 minus ln. Now we need to do the same thing with 1 over root 2. Well, if arctan, you know, if we're talking about that first one, tan of arctan of 1 over root 2 is just 1 over root 2. Yeah, but if I had 1 over root 2 up here and I squared it, I'd have a half. 1 plus half is 3 over 2. So this would actually be root 3 over root 2. And hopefully this will give us the answer according to the formula, according to the mark scheme. It's 0.345 or something. They didn't want it exact, but you know, we got it exact. So aren't we great? Root 3 plus root 2. I'm just checking it right now. Minus ln of, there I go, tapping on my calculator. 3 divided by 2 plus root 1 divided by 2. Okay, it's not come out right. Oh, it's because I called it 0.5 rather than 1 over root 2. 1 second. I'm so useless with a calculator. You've seen that in class, haven't you? So let's write this as, oh no, I'm so bad with this. What is 1 over root 2 roughly? Is it 0.707? Can I just find it roughly? Oh, I'll just call it root of 1 divided by 2. That would be probably a quick way. 0.345, yes. So we got it right. That is absolutely correct. So that's a crazy way of doing it. But that way, at least we covered that kind of technique in class. But you would have been well within your rights to just use the R-Shine formula here. You know, absolutely. So thank you for putting up with my dawdling explanation to that last one, because, yeah, I wouldn't have done it like that in exam conditions. But, you know, what was I doing? Maybe I was just showing off or something. I don't know. Anyway, hope that's useful, everyone. Best of luck with the test coming up, gang. Watch out for everything that you've done. You know, there's some tough integration we've done. There's some tough complex numbers. There's some tough polar stuff. We've done some tough stuff, basically, haven't we? Watch out for method of differences and everything else. Anyway, all the best, and have a lovely half term. Bye-bye.